There we go. There'll be a lot more people fighting for exam spots in that final exam time. You know, exam 1 and exam 2 fall on non-midterm weeks, so there's really no fighting for positions. But final exams, every online class is there, and us. And I have 2 different online 123, so now you're on the same schedule. So get your appointment done early so you can get the day and the time that you want. But again, I will be sending out an email later today to remind you of all of that business. So, does anybody have any questions before we get started on the new stuff? What is happening? Okay, well, no questions. If you have them, you know, go ahead and throw them at me later. But we will go ahead and just jump into 25 and 26. So 25 and 26, as I said, kind of go together. We're dealing with linear models and scatter plots. So we'll spend the majority of today on linear models, which is section 25. And before I start talking about what all of this stuff is, can you, if I just say linear models and think about the words slope, y-intercept, or the model itself, does anything come to mind? And you can either type it in the chat box or go ahead and just shout it out if you unmute yourself. But anything that comes to mind, we're playing word association right now. Word association. A line graph. Yeah, so when we're talking about linear models, if we graph those things, we are totally going to have a straight line. So we are talking about line graphs. Yes. Anything else? Okay. So we're starting from ground zero. That's okay. All right. So a linear model, the word model implies the equation. So we're going to write linear equations that show or predict the line, right? So as Brooke mentioned, we have line graphs here. Our job is going to be to write equations that describe these lines. And to do that, we are going to need the slope and the y-intercept. So this first part here is just the introduction. What do all of these pieces mean? And if this stuff is either new to you or it's been a long time, I would recommend watching all of the videos for this, because the more you do, the easier they get. And there are a lot of extra examples of this in the back of your packet with the 080 material. There are videos for those too. But again, the more you do, the easier they get. Okay, with that being said, slope is often referred to as rise over run. All right, so you may have heard that when slope is first introduced, this is how we describe it. Okay, and let me, if I have a graph here, I need to change color so we can easily see what's going on. Let me get a pink line. Okay, so to find the slope is a constant change. So the same change happening over and over and over and over. And when I say rise over run, I mean rise going up, and then the vertical change over the horizontal change. And then we would have a vertical change over a horizontal change, and a vertical change over a horizontal change. And so you can see where my green line touches my pink line. Those are all dots or points on my line. So when I say rise, I'm talking about the vertical change, right? So we're talking vertical change over horizontal change, because that's what rise is. Rise is vertical, running. If you run, you're covering horizontal distance. Now, if I think of that in terms of a graph, vertical, this is the y-axis. Horizontal is the x-axis. So vertical change means the change in the y values. I'm abbreviating change with CH, by the way, because I'm lazy and it's hard to write with this thing. And horizontal change would be change in the x value. Okay, so we've got vertical change over horizontal change, which corresponds to the change in the y values over the change in x values. And now comes my first question to you. In mathematics, when I say the word change, what does that mean? What mathematical operation is noted by the word change? Think about if you go to the grocery store and you're going to buy something. You buy $5 worth of groceries and you give them a $20 bill. How do they figure out how much money you're getting back in change? They subtract, right? Shannon threw that in there. Yeah. So we're going to take the subtraction of two y values, because that's what change means, and then we are going to subtract two x values. Now, if you see these little ones and twos next to them, those simply mean that is an ordered pair. So x1, y1 is an ordered pair. x2, y2 is an ordered pair. So those little numbers have no value mathematically. I call them, they're like a wedding ring. X2 and Y2 are both wearing the same wedding ring. They are together. They belong in the same ordered pair. So we need two ordered pairs in order to find our slope. Okay. Now, it doesn't matter when you give ordered pairs these, X1, Y1, X2, Y2. It doesn't matter which is which. And we're going to show here in a little bit why that is true mathematically. But this formula for slope, y2 minus y1 over x2 minus x1, that is on your yellow formula sheet that you get for the exam. So just FYI. Okay, so that's kind of your basic thing about slope. But let me change color just for effect. So remember that slope is I need the word reoccurring change. It happens over and over. It's a constant rate of change. If you want to use words, rate of change. But it's reoccurring. It happens over and over and over and over. So when we read problems, if you identify something, you're like, wow, that happens over and over and over again, boom, there's your slope. Okay, because the slope just constantly happens. All right, let's move on to the y-intercept. If I have myself a graph, now I've drawn a green graph. I'm going to put myself a blue line. And with my red pen, you will see that my blue line crosses my y-axis at that one point. That there is my y-intercept. So it's where your graph crosses the y-axis. How many y-intercepts will we have in a linear model? Just one. Exactly. And that's one thing to keep in mind. You're only going to have one y-intercept. So whereas the slope is reoccurring, you have a ton of those, right? It happens all the time. The y-intercept is just a one-time thing. Okay, so with the y-intercepts, so this ordered pair for that red dot might be 0, 2. All right. Now if I draw another graph, we'll make it orange. And it goes right there. That ordered pair would be 0, 0 the way I graphed it. Let me graph one more just for fun. We'll make it down here, and that y-intercept would maybe be 0, negative 2. What do all three of those y-intercepts have in common? Zero, exactly, and even more specifically, good, x is 0. That has to be true. In order to have a y-intercept, you must have an x equal to 0, because your y-axis, that's where x is 0. So if you want your graph to cross the y-axis, then the x value must be 0. And that's something we're going to have to keep in mind. So there you go with that. What am I missing? What am I missing? Slope is noted by the letter M. Y-intercept is noted by the letter B. Where did those come from? I have no idea. I'm sure some dead Greek guy came up with that when he was deciding how to make math harder for people. More than likely, that was it. So, okay, so there's kind of your basics of slope, your basics of the y-intercept. We will talk more about those as we work through these problems, and you can kind of see how they matter or why they matter. All right, so now the model. I'm sure you've all seen this model before. Y equals mx plus b. So, just to reiterate, here's your slope. This is your y-intercept. X and y will always stay x and y because they represent every point on your line. So when you're writing your equation, you should have y equals a number for your slope, which can be positive or negative, times the x value, and then either plus or minus b. because you can have a negative y-intercept. So if you have, as we showed over here, the gray dot has a y-intercept of -2. So in the equation, it would be a -2. In red, it's a +2. So in the equation, that would be a +2. So whether or not your y-intercept is positive or negative, that will determine in your equation whether or not it's positive or negative. Okay? And again, we will do plenty of this. But this, again, is called the model. So when you read a problem and they say, what is the model? They're looking for an equation. And when you have an equation, you should have two variables, an x and a y, called an independent and a dependent variable. Y will depend on x. Okay? All right, so that's kind of just in general. We will talk more detail as we work through problems. Any questions on this basic introductory page? Going once, going twice. Okay, hey, thank you for replying. That's fabulous. I love interaction. That's great. Okay, so let's erase that. Let's move on. So this, I call this a very straightforward problem, and it's straightforward because they give me the information. So the cost of a cell phone plan is $30 a month plus 10 cents a minute. Okay, so if we take that, they give us two pieces of information, $30 a month, 10 cents a minute. And we're talking about the total cost. How often do you pay your cell phone bill? Monthly, exactly. So we're talking about the cost. So we're talking about a 1 month bill in this problem. Just keep that in mind. Okay, so what do you notice about the 10 cents or the $30? Do you notice anything about it? Can you tell me, slope, y-intercept, anything based off of what you know? Which one of those things happens one time? Just once. Do you pay the $30 one time, or do you pay the 10 cents one time in a month? $30, right? So this is the monthly fee. So this happens one time. So one time is what? If something happens one time, what is it called? What's our math term for that? It's the starting point, right? Even if you don't use your phone at all, if you have this, you pay a $30 monthly fee. So that's our starting point. So that would be our think back to the previous page. What happens just one time? No, not getting this. No? Okay, so you see how $30 a month is happening one time. There you go. So it's our y-intercept. 10 cents per minute. So this happens over and over and over and over and over and over for every minute that you talk. So this would be my slope. This would be my y-intercept. So that's kind of how you can tell when you read a problem what happens one time and what happens over and over and over again. So my slope is 10 cents. My y-intercept is $30. And we're talking about the cost of the cell phone plan. So they're both positive because both of those things make my bill go up. All right, so I know that M is 0.10, and B is 30. Okay, how can I put those together to make my equation? Okay, so we're going to start with, remember the model is y equals mx plus b, and that is also on your formula sheet. So we start with y equals, what's my slope? .10, and then attached to that, we multiply that by x. X, we're going to talk about that next. I'm getting ahead of myself. And then we have our y-intercept. There we go, Amanda, plus 30. So think about it. If you don't talk at all, 0 minutes, 0 times anything is just 0, and 0 plus 30 is 30. So that's where your y-intercept comes in. That's your starting point. Because when you haven't done any talking on the phone, your bill is still $30. Okay, so now we get to letter D. What do X and Y represent? Okay, well, when you're thinking about X, so let's start with X. First of all, look at your problem. X is connected to your slope. Well, what does your slope represent? Well, that's 10 cents per minute. So what do you think X is going to represent? Perfect. X is the number of minutes on the phone. Yes. And that should hopefully make sense. If you're paying 10 cents per minute, well, if I talk for 10 minutes, I multiply 10 cents times 10. There's my, that's how much I use. So X, if you ever have a problem that talks about time in any way, shape, or form, X is always going to be the time because everything depends on time. But if you don't have time, it's a whole different story. Okay, what does Y represent in this story? If X is the number of minutes, slope is the price per minute, 30 is your monthly fee, Y is your total what? Total cost. There you go, total bill. Very good. Very good. You're not going to see a question like D very often where you have to actually give that information, but it's really, really, it's crucial that when you're writing these, you understand what X and Y represent because you are going to have to answer questions like E and F. And if you don't know what X and Y represent, it's a little bit harder to answer questions E and F. So let's go ahead to those. What is the monthly cost when you talk for 76 minutes? What do I do with that 76? You put it where X is, exactly, because 76 minutes is represented by X. So I have Y equals 0.10 times 76 plus 30. And we have 3760. And this right here is the whole purpose of linear models, is to be able to predict all kinds of different pieces, right? So sometimes you can predict that way. If I talk for 76 minutes, it's going to cost me $37.60. Or you can go the other way. My bill was $43. How many minutes did I talk? So how do we figure out letter F? What do you do with that 43? You put it in for Y, because Y represents the total cost. So let's go ahead and talk through this one. How do I get X by itself? What's my first step? Subtract 30. Good. Both sides, subtract 30. So that means I'm left with 13 equals 0.10x. And my last step to get X by itself, divide. Good. So we're going to divide by the number in front of X, which is the 0.10. And therefore X is 130 minutes. Okay. So you can use it both ways to find information, but you have to have the model set up first. Okay. All right. So I call this a straightforward problem because they give you the slope and the y-intercept. You just have to decide which is which some days is easier than others. But if you can remember, y-intercept happens one time. Slope is recurring. It happens over and over and over. So if you can remember those two things, you should be fine. All right. Any questions over this problem? Okay, again, the more you do, the easier it gets. I do recommend you do a few more after class is over because we're going to do 2 problems and, maybe 3. I have an extra example with, yeah, we'll figure it out. Okay, The population of a town in 1970 was 5,600, and in 1995 it was 4,100. Okay, so this one is a whole lot more work for you. So we're going to do that. Now, in order to part B, find the slope, and then in part C, write the linear model, we need two ordered pairs. So our first order of business is to create two ordered pairs. Now, just in general, you can see that the population in 1970 was 5,600. I mentioned earlier that if you have anything that references time, that's going to be your X value. So I could have one ordered pair that is 1970, 5,600, because in 1970, my population was 5,600. And then my other one would be 1995, 4,100. But this provides us with an extra problem. Problem being, I know that in part C I need to write a linear model. And to write a linear model, I need a y-intercept as well as my slope. Now I can find a slope through those 2 points, and we will here in just a moment, but I don't have a y-intercept yet. What must be true for me to have a y-intercept? X has to be 0, exactly. And right now, the smallest X I have is 1970. So what we're going to do, and this is totally legal, like I don't just make stuff up, this is totally legal, is we're going to say, okay, let's let 1970 be X equals 0. Because 1970 is my oldest year, right, my earliest year, so that's my starting point. And our y-intercept is our starting point. So I can change this ordered pair to become 0, 5,600. Because in that first year that we care about, 1970, the population was 5,600. Okay, but now think through your mathematicness. If 1970 is X equals 0, what's 1995 going to be? $25, exactly. Because you're thinking, how many years later is that? So sometimes it helps if you actually write them down just like I did. So from 1970 to 1995, you can subtract. There's 25 years. So X is going to be 25. So now I have new corresponding ordered pairs. They're going to give us the same slope. And now we also have a y-intercept. What is my y-intercept? That's not one of these questions, but I'm asking it anyway because I can do what I want. Okay, Shannon, you have, when X is 0, you have a y-intercept. What is the y value when X is 0? Because remember, ordered pairs always come in the order X, Y. So when X is 0, this is my y-intercept. So X is 0 here, so my y-intercept is 5,600. Because that's the y value when X is 0. So that was the sole purpose of rewriting those ordered pairs so that we could have a y-intercept. Okay, so we have created two ordered pairs with an X value of 0. Now we need to find the slope. So recall, slope is y2 minus y1 over x2 minus x1. So it doesn't matter which way you do this, but if we say that this is x1 and this is y1, and this is x2 and this is y2, okay, and I meant these go to the yellow one here. So what's my first y value I'm going to play with? What's the value of y2? 4,100, okay? And then we subtract y1, what's the other y value? 5,600, okay? In the denominator, you want the ordered pairs right on top of each other. So what is the x value that corresponds to 4,100? 25. And my other x value is 0. So now we mathematize this process. Do a little subtraction. What's my numerator? Negative 1,500. And our denominator is 25. If you can simplify, you should. So this just comes out to be negative 60 over 1. Now, for our model purposes, you don't necessarily need a fraction. But if we want to interpret, because you will be asked to interpret your slope, think about what this represents. All right, so the numerator is the y values. Y values in this case represent population. And the x values on the bottom talk about years since 1970. Well, a negative slope means that our population is going down, right? Exactly, Amanda, it's a decline in population. So, yeah, it goes down 60 every one. Exactly. Yes, so you guys already understand how to do this. I love labeling my slope on the numerator denominator because then it's totally easy to see. You see the population decreases by 60 for every 1 year since 1970. So every year, 60 people are either leaving or dying, right? Because that's the change in population for every year. But notice it's only since 1970. We don't know if this continued on before 1970 because we don't have that data. We only know from 1970 to 1995. That's all we have. Okay, so you will be asked to interpret a slope, so just prepare yourself mentally for that. All right, and now we need a linear model. So what does our equation look like for this? Very good. Y equals, our slope is negative 60 attached to x, and then our y-intercept is 5,600. I guess I should put my slope up here, negative 60. All right, and the x represents years since 1970, right? Because you have to remember you're keeping that because of the whole 1970 and 0 business. X is the number of years since 1970, and Y is the population. So when we get to letter D, use that model to predict the population for 2017. What do we got to do there? Okay, Brooke, absolutely right. We're comparing. Amanda, you don't want to use a proportion. You want to use your model. You want to use that equation. But the deal is, and Brooke had it in there, we know that x equals 0 for 1970. And we're looking at 2017, so what is x? So if you subtract 2017 minus 1970, we get an x value of 47. And then, yeah, don't work any harder than you have to, right? Keep it as simple as totally possible. You want to make it harder, don't do that. So once we know that x is 47, then we just go to our model and say, okay, negative 60 times 47 plus 5,600. So then we can just use the model that we wrote in part C. I did not get 3680. Did anybody get something else? Yeah, 2780 is what I got. So Brooke, you might want to see what you typed in. You might have hit a wrong number somewhere. Oh, yep, that'll do it. Yep. Easy fix, easy fix. All right, so this is about the most intense problem you're going to see. Because in this one, you had to first write your ordered pairs, change one of them to have a y value or x value of 0, so you had a y-intercept, write the model, find the slope, use it. Right, so that has all of the pieces together. If you can do that, you're golden in this section. All right, let's see what the next page brings. The state of Indiana has a goal of 60% degree attainment among adult Hoosiers by the year 2025. If the percent of Hoosier adults with degrees was 33.2% in 2010, construct a linear model to estimate the goal for each year. Okay, so that's your first order of business. Here's one set of data. Here's your other set of data. Okay, so it's just like what we did. Now, even though these are percents, they're just data values. Just like we talked about in section 24. They're just data values. Okay, so I want to give you guys a few minutes, see what you can do with them. So you're going to need 2 ordered pairs first. You got to find your slope. You got to find your y-intercept. But it all starts with ordered pairs, okay? So I'm going to give you a few minutes, see what you can come up with. Let me know if you have questions, but there you go. Okay, so let's go ahead and work through. Yep, you're good, you're good. Okay, so let's go ahead and talk through the process, because not only you guys who are in here, but people watch this later, so I want to make sure we have this process. So in talking about our 2 sets of data, which one did you use for your x equals 0? All right, just talking this through for everybody who's watching it later. We used the oldest year of 2010. So that makes this ordered pair 0, 33.2, using those data points as values. Great. What does that make our other ordered pair? If 2010 is 0, what's 2025? 15. So I have the ordered pair 1560. All right, good. Now that we have those two, the y-intercept should just jump out at you. What is your y-intercept?
Would it be 33.2?
It would be 33.2. Remember, the y-intercept is always the y value when x equals 0. So it's just 33.2. That's it. And it's positive, which is a good thing. Okay, so then we go to the slope. So we need to find slope. You can do it one of 2 ways, right? It's either y minus y over x minus x, or you could have done 33.2 minus 60 over 0 minus 15. Either way, and if you don't believe me, do the math. Either way, what is your slope? And go ahead and round it if you'd like.
And I got like 1.7866, so I just did 1.8.
Yeah, 1.79 or 1.8, something like that is good. You would end up as a fraction 26.8 over 15, right? In this one, it's negative, and in this one, they're both positive. But we all know that 2 negatives is a positive, which is why they're the same. So, okay, so if we use a 1.79 or a 1.8, either way, it doesn't matter. What is our linear model that goes with this? So this is the process. You find your slope, you find your y-intercept, then you can write your model. What does your model look like?
Y equals 1.8 or 1.79 x plus 33.2.
Perfect. And if you find that you get lost with all of the numbers on your paper as you're working through things, do this up here. Just give yourself a spot where you write your slope and your y-intercept, because once you have that, the model is fairly simple, right? You just plug those numbers into the 2 spots. Good, so that's letter A. Now we get to letter B, where it says, use this to predict for 2016. What is this going to tell you, or what do you know? How are you going to do this? 2016.
We need to subtract 2016 from 2010.
Exactly. Since 2010 has an x value of 0, you're thinking, okay, from 10 to 16, how many years is that? So what would my x value be? What's 2016? Oh, 6, there it is. I got so used to you talking, then all of a sudden you type. Yeah, so x is 6. So we go to our formula. y equals 1.8 times 6 plus 33.2. I'm going to have to depend on you guys for an answer because I used 1.79 for my slope. So my answer is going to be slightly different than yours, which is totally fine.
I got 44.
44. And that should have a percent sign on it, right? Because that we're talking about percent of degree attainment. So in 2016, degree attainment should be 44. Yep. How'd you guys do on that problem? Do okay? Good. Good, good, good. All right, so that's section 25 in a nutshell. All right, and again, the more you do them, the easier they get. I definitely recommend you work through a few more out of your packet before you jump into the homework. It'll just make life a little easier. So, and when you get to the homework and web work, a lot of them give you this information, and then the question is, use a model to predict the year. So the only thing you're going to put in is the final answer. Well, if your linear model is wrong, then everything's going to be wrong. So if you have a question, you send it to me, make sure you're sending, hey, this is the model that I'm using. That way I can say, ooh, that's your problem. Okay, it's just a lot easier to kind of help you out if I know what you're using. So, okay, section 26 gets us into scatter plots. And we're going to have time, I think. I'm going to bring up Excel so that we can use that. But in a nutshell, a scatter plot is simply a graph that has a lot of dots on it. Okay, and it just graphs the change in things over time. So we have dots, okay, where the x-axis is generally time and the y-axis is whatever it is we're talking about. Now, a trend line is a line, straight line, that cuts through the middle of your scatter plot. So sometimes this is called a regression line or a line of best fit, anything like that. So, but it's a line that basically cuts through all of these dots. And it's what we use as an estimate for, because when you have dots all over the place, you can't really estimate things. But if I throw a trend line in the middle, now I have a linear model. And that linear model, I can use that to predict things. So this trend line, right, will have an equation, a y equals mx plus b equation. And by the way, Excel is beautiful and it will do this stuff for you. So you have this, Excel gives you the equation, and then Excel also gives you r squared, and it'll give you a value for r squared, right? We'll just go with, make this up, right? R squared is called the coefficient of determination, which is not important for you because we don't care about r squared in this class. In this class, we care about the linear correlation coefficient, which is noted by the letter R. So our first step, before we even talk about what R is, let's talk about the mathematics of it. If they give you r squared, what is the mathematical step to go from r squared to r? How do you unsquare something?
Take the square root of it.
Take the square root of it, exactly. So we're going to square root both sides because we don't care about the coefficient of determination. We care about the linear correlation coefficient. So if I square root r squared, I just get r. And if you take the square root of 0.7541, what does that give you? You really should write this stuff down. 0.7541. Here's the
0.8683, a whole bunch of stuff.
Whole bunch of stuff, exactly.
Yeah.
Yeah. So just make sure you're paying attention to what's around to. But there you go. Now, one thing about the linear correlation coefficient, it's always going to have the same sign as your slope. So one thing that we haven't really talked about much, this green line that I drew goes up, right? So this is a positive slope, so my linear correlation coefficient is positive. Now, I'm going to draw this picture up here. Let me change color for effect. This line is going down when I look at it left to right, so it has a negative slope. So if this was the linear correlation coefficient to go with this yellow line, we would have to throw a negative sign in front of it. Your calculator is always going to give you a positive value for r, because when you take the square root of something, it's always positive. So you're going to have to manually type in that negative based off of, do you have a negative or a positive slope? So keep that in mind. Okay, now the purpose of R, because it does have a purpose, this tells you how good of a fit your line is to your data. So the closer your dots are to being perfectly linear, the closer your R value is going to be to 1. So like this is 0.8684. That's not too bad. So we would say that we have a, I don't know, I would call this a somewhat strong linear correlation between whatever two variables we're comparing. It simply means that the dots are pretty much in a straight line. You know, we have a few that are, you know, stragglers off of that line, but for the most part, they're very good in terms of being in a straight line. Okay, this is all that there is in section 26. It's more slope, it's more using equations to predict, but this is all the only new stuff that we have. Okay, so what I'm going to do now, I need to erase all of that. I want to bring up Excel. And we're just going to do a real quick business here. So if I get some years, let's go 1990, 1991. Let's autofill for some years. And then let's just type in so those are pretty good. Okay, now if I highlight these, so I have two sets of data, you notice that my time is the X value. I'm going to go into Insert. You see all these dots up here. So there's my scatter plots. There it is. Okay, so from here, if you see the plus sign on the right, this is where we can add a trend line. So there's my they just throw it in there. Now, if I double click on that trend line, it brings up all this crap on the right, and it says Format. At the very bottom, display the equation and displayed R squared. So we can see my slope is 0.1758, and my R squared value is 0.0341, which means these are not very close to being linear, is what that means. So from here, then I could interpret my slope. We're talking about mice in my basement. The number of mice in my basement has increased 0.1758 for every 1 year after 1990. Right, that was my interpretation of my slope. If we wanted to find the R value, again, remember that for that we would have to take the square root. So we would take the square root of 0.0341, which is something not very big. 0.0341 square root. So our R value is 0.1847. I would say there is pretty much no linear correlation between mice in my basement and the years after 1990, because that is a super small value of R. Okay. Now, with Excel being as fabulous as it is, if I would change one of these values, erase my... Notice how when I changed one value and hit enter, it readjusted. It readjusted my trend line, it readjusted my R value, and everything. So section 26 is pretty much given, you're given this information, and now you get to play with it in talking about the linear correlation coefficient and whether or not you have linear correlated data or not, is pretty much what it comes down to. So there's that. Okay. That's all I really have for these two sections. Do you guys have any questions?
I have a quick question. Sure. When we do the R and get like the square root of R, when we get that, is it the bigger the number, the better, or lower the number?
Well, it honestly depends on what you're looking for. So the closer it is, so R in general is going to be somewhere between -1 and +1. It can't be bigger than 1. It can't be lower than -1. So if you have, like in this case, our line goes up, so our R value is going to be somewhere between 0 and 1. If it has a value of 1, that means our line, our dots are perfectly linear. Obviously, the graph that we're talking about on here is not. So if you're looking to show that there's correlation between these two variables, then you want it to be close to 1. But whether it's bad or good, it just shows whether or not your dots are in a straight line. That's what it's showing you. So the closer to 1 it is, the stronger correlation you have between the two variables. Anything above 0.5 shows some correlation. A super strong correlation is above 0.9. But whether if that's what you want, I don't know. So if we have a graph and it's going down, then our R value will be somewhere between -1 and 0 because it's negative. So again, if you're at like -0.5, between -0.5 and -1, then you have some type of negative correlation because our graph is going down. But yeah, it's a whole lot easier if your R value is closer to 1, because then you know that you have a strong correlation between the things.
All right, that makes sense. Thanks.
Yep. Other correlations, other questions.
I have a question about the final.
Okay.
For the third exam. Last exam I had asked to use headphones and he had to call you for permission. Will we be allowed to use them on exam 3?
As of right now, no, because that's not checked.
Okay.
Is there a good reason for headphones?
It helps me focus because I feel like there's so much extra noise in the library while I take my exam.
Yeah, I can send an updated form for that. Brooke, do you need headphones when you take an exam?
No, I'm usually pretty good at just tuning everyone out.
All right, in that case, I'm going to make it just a single exception for you, Shannon, since you asked. Nobody else has asked.
Okay.
Brooke is here, so I asked you, and Crystal is now active, I think maybe. So Crystal, if you want headphones, you gotta ask now. But everybody else, I guess, if they watch this, they can email me and ask. But otherwise, yeah, I'll get that form turned in today, and then it should be okay for you from there.
Okay. Thank you.
Yep. Thanks for asking. Any other questions? And again, I will be sending out an email later with all of the directions for exam 3 to kind of get that going. We only have 2 sections left after this, and they're pretty easy sections, which I am super thankful about. So they're good ones to end on. They're pretty easy to catch on to. So we'll talk about those next week and kind of get any other questions for the exam out of the way. But yeah, then you're good to go. So you can start that review quiz anytime because the highest grade is kept. So yeah. All right. If you guys don't have any other questions, though, I'm good to go. So go have a good day. And if you have anything else, you know where to find me.
I feel like this year went by so fast.
Yes. This semester has flown. I mean, next week is May. That to me is just crazy.
That is crazy.
Yeah. But it's good.
Mm-hmm.
Been positive. So, yeah. All right. Thanks for coming and participating. I appreciate it.